All right. Well, I have put off the homework that was due tonight because I didn't finish the section last time. It'll be due on Monday, so don't worry about that. This is the last part of the section. Last time we did global maxima and minima. I'm sorry, local maxima and minima. And this time we'll do global maxima and minima, right? What's the difference between a local maximum and a global maximum? Just similar to calculus 1, right? In calculus 1, you could have the same thing for a function of one variable, but here's a surface, for instance, z equals f of xy over some domain D in the xy plane. And here, maybe at the bottom of this well here, this little tiny well is a local minimum, but it's not the minimum of the whole function. The minimum is clear over here. So a local minimum means over a little region in the xy plane about a particular point. You have the portion of the surface up here. The smallest z value occurs at that point. So a global maximum means over the whole domain of the function what's the highest point and the lowest point. So that's what we want to talk about today is how do you find the highest over the whole function and the lowest? It might wobble up and down and have a highest up here, and all these other local maxima where you have a peak of a mountain don't matter for global purposes. So here's the definition, and we had this right at the end before. If you have a function f of xy, f of x naught y naught is said to be a global maximum or a global minimum alternatively. If f of x0, y0 is bigger than or equal to f of xy for all xy in the function, right? So it's just like calculus 1, a function of one variable. Maybe I should draw that on the side. Calculus 1 analogy. You could have something like this. On interval AB, and you'd say, oh, this is a local min, but it's not the global min, right? The smallest y value of the whole function y equals f of x is right here. So the global minimum was f of x0. This is a local minimum, but it's not a global minimum. Here's a local maximum, but it's not the absolute maximum. The absolute maximum occurs at an endpoint. So here's the absolute or global maximum. Here's the absolute or global minimum. And here are some local maximin that aren't global maximin. Similarly here, the surface might have a little local minimum here, but the global minimum, the smallest over the whole surface, is way down here. And the global maximum is right up here, the highest z value. So that's all it means. The highest z value over the whole domain is the global maximum. The lowest z value is the global minimum. Then you also want to find what point does it occur. So the global maximum is at x0, y0. Here, the global minimum at x1, y1. That makes sense for the definition? I hope. And then a point or a value that's either a global maximum, global min, is called a global extremum. And they also have the name absolute extremum. So absolute extremum or global extremum mean the same thing. Just different books use different terminology. Now, how did you find a global maximum and minimum in calculus 1? Here's the picture. This was the most important case. There are certainly other cases you do sort of on a case-by-case basis, but if you happen to have a continuous function on a closed interval, a to b, right? Then there was a theorem that said it had an absolute maximum, which makes complete intuitive sense, right? A continuous function intuitively is one you draw with a single stroke of the pen. So if I draw a single stroke of the pen from point A to point B, I'm going to have a highest point I go to and a lowest point I go to, right? Here, the minimum is y1 at A, an endpoint, and the maximum is y0 at C, a critical point. You had a theorem also that said the theorem continued, every continuous function on a closed interval has a global maximum and it occurs either at an interior critical point or at an endpoint. Now we've got a nicely analogous theorem for functions of two variables, such as here. This is what we had up there. Here's your surface again over a domain. And it says, let me slide this down a little so you can see the bottom. I hope. Can't do it. There we go. The theorem for calculus 3 says a continuous function z equals f of x, y of two variables has a global maximum on a closed bounded domain. What does closed bounded domain mean? It means, closed means it includes all its boundary points. Bounded means that it doesn't go out to infinity everywhere. Formally, what you say is there's some circle of finite radius that includes the entire domain. So I can make a big little circle of the origin and D would be inside it and it's bounded, right? That's what closed and bounded means. And it's just like here, if you have a closed bounded interval, then there's a maximum and minimum on the interval, similar for a continuous function. Similarly here, if the function of two variables is continuous on a closed bounded domain, then it has a max and min. Furthermore, it's got an analogy here. The global max and min that occur, it might occur at more than one point, but wherever these occur, they're always either at interior critical points or at boundary points. So here, for instance, for this surface, there's a highest z value of global maximum at this point, x naught, y naught, right? Of f of x naught, y naught is the maximum. So the z coordinate is the maximum, occurs at this point. And then the minimum occurs at x1, y1 at along the boundary point here, right? And so that's the concept. Continuous function on closed bounded region. It's just one more dimension of what you already did. Any questions on all that? That's the big theorem there. And then there's some homework problems that ask you to figure out what is a closed bounded domain. And there's some set notation you should be familiar with too. Suppose I did this one. Suppose I consider now which of these are closed bounded plane regions so that I could apply the theorem if I had a function defined on these. Everybody knows what a closed interval is, but what's a closed bounded plane region? Suppose I gave this one. You're familiar with this set builder notation? I've used it very briefly before. These braces mean the set of, right? And then the word all is assumed. All ordered pairs x, y is what this is. This means element of, or element of a set. And the set here is R2. This means R Cartesian product with R is R2. The set of all ordered pairs of real numbers. We're saying the set of all x, y that are ordered pairs of real numbers. The colon means such that. I like to put a straight line. Other books will use that. So a straight line or a colon means such that x squared plus y squared is less or equal to 9. That's all that notation means. It's set builder notation, they call it. Is that a closed bounded region? What region is it? How do you draw it? That's the easiest way to figure it out. Try drawing the boundary. When you have a continuous function like this, you can draw the boundary, and then the inside of the boundary, either every point will satisfy the inequality or not, and the outside of the boundary, every point will satisfy it or not, because it can't jump suddenly from being less than 9 to greater than 9. It has to go through the boundary to change. So what does x squared plus y squared equal 9 look like? Well, that's x squared plus y squared equals 3 squared, right? So it's a circle of radius 3 at the origin. That's the boundary. drew it solid, why did I draw it solid? Sometimes I draw these dotted. If it's a non-strict inequality, I include equals, that's going to be in the domain. So if I have equals here, then I draw a solid curve indicating that's part of the domain. Now I check a point interior to that circle, 0, 0, and 0 squared plus 0 squared is less than or equal to 9. So 0 is the solution of this inequality. That implies that every point in this inside this circle is a solution. So these points are all in the domain. And then you can check a point outside. And I think the points outside also satisfy sometimes. So I'll go out here maybe to 5, 0. 5 squared plus 0 squared is not less than or equal to 9. This point is not in the domain. You conclude that every point outside the circle is not in the domain. So the domain actually is this disk. The interior of a circle is called a disk. The open disk, if you don't include the boundary, the closed disk means you do include the circle as the boundary. So this is a closed disk. The boundary is a circle. And the domain is a closed disk. Closed because it includes its boundary. Since it's a closed bounded region, you could apply the theorem to the function defined on this region. How about this one? Suppose I took the set of all x, y elements of R2 such that x squared over 4 minus y squared over 9 is less than or equal to 1. How about that one? Well, if you plot x squared over 4 minus y squared over 9, what's that? That's the boundary. I mean, what does it look like? That's actually a hyperbola, right? Remember that from conic sections. With a equal 2 and b equal 3, and we know how to sketch it, and so it's going to look like this. Going to go up to 2 and back to minus 2. And it's going to have asymptotes plus or minus 3 over 2. 3y equals 3 halves. Y equals minus 3 halves. And then we can check points again. If we put 0 into the inequality, 0, 0, 0, the origin, just to pick an easy point. 0 minus 0 is less than or equal to 1. So the points, the origin is in the domain. All these points in here in the domain, because this is a continuous function, all the points between these boundary points will be in it. Now we can try to point out here like 3, 0. Well, let's see, 9 over 4 minus 0 over 9 is not less than or equal to 1. And also we try minus 3, 0, and that's not in the domain. So all these points out here and out here are not. This is the domain. This is closed because it includes the boundary, but it's not bounded. It goes out to infinity. Right? Oops, sorry, I put it off the bottom. Tell me why I'm doing that. So, how about this one, C? Well, I have the set of all x, y. Such that in R squared, you don't have to write that x, it's normally assumed, but such that x squared over 4 plus y squared over 9, same thing but plus, and then we'll say is strictly less than 1. How about that? So is that closed bounded region? Now what you do is you say this is an ellipse, right? Sorry, if I draw the boundary, it's an ellipse. X squared over 4 plus y squared over 9, the boundary equals 1, is an ellipse. So I draw it in the xy plane with semi-axes 2 and 3. And it'll look something like this. Oops, except I already boxed it. What did I mess up there? This time I don't include the boundary because it's a strict inequality. So these points on the boundary are not part of the region. I have to draw this dot, and I should have drawn a dot like that. And again, to be less than 1, I have to include the interior. Right, 0, 0, you plug it in as a solution, but out here, like 3, 0 is not. So this is your domain D this time. And this one is bounded because I can find a large disk that includes all these points that doesn't go out to infinity. But it doesn't include its boundary, so it's not closed. So this is bounded, but not closed. So again, you can't apply the theorem. And the idea that you need to have this for is like you see in this first picture. If this is my domain and I don't include the boundary, then I might get closer and closer and closer to the smallest z value, but because the boundary is included, I'm never equal to it. Like maybe this is z equals 4, you can't say that's the minimum. The function never takes on 4, or whatever this value is. You can call this an infimum of a greatest lower bound, but if the function is never equal to 4, then it doesn't have a minimum. So when you have a region that's not closed, sometimes you get closer and closer to a minimum but never reach it. Similarly, if the region is not bounded, then you can just keep going up forever out here with a continuous function, and it never reaches the highest point, or it might go down forever and never reach the lowest point. So that's why you need the closed bounded region. All right, I hope I didn't spend too much time on that. That's actually the easier part of the lecture today. But the idea is on a closed bounded region, such as this first one, a function defined on there will have a largest value and a smallest value. And what's more, it's going to occur at an interior critical point or at a boundary point. So now we can apply that to actually solve the problem. And this first one I want to do is very important if you're a business major. Finally, there it is. Let's try this one. Suppose I have f of xy equals 5x minus 3y plus 34. And that's my function. And it's defined on a domain, D, let's say, which is a set of all x, y. I won't put an element of R2 this time. They'll be assumed. Y greater than or equal to x minus 2. Y greater than or equal to minus x minus 2. And y less than or equal to 3. Part of this problem on these things is being able to sketch the domain. What does that look like? Oops, what does that look like? Well, you can sketch it very easily, right? What kind of figure is this that I put up here? First of all, is it continuous? So I can apply the theorem. The theorem says you need a closed bounded domain and a continuous function. How do I know that's continuous? Well, I write out what it is, right? This is z equals 5x minus 3y plus 34. You can rewrite it as 5x minus 3y minus z plus 34, page number, equals 0. And that's a plane, right? A plane is a nice continuous function. Moreover, I'd like you to recognize in all these problems, most of the problems at least, the functions are polynomials in 2 variables. This is a polynomial in 2 variables, right? Whenever you have, like this, a number times the power of x times the power of y plus a number times the power of x times the power of y plus blah, blah, blah. Number times the power of x, number times the power of y plus a number. You call that a polynomial in two variables. And these are all those cases. Think of this as times y to the 0, this times x to the 0, if you like. Each one is a number times the power of x times the power of y, all added together. Those are continuous, just like in calculus 1, a polynomial in one variable is continuous. A polynomial in two variables is a continuous surface. And so this plane, even if you didn't recognize it's a plane, you already know this is a polynomial, it's continuous. But certainly, you know, from the picture, I guess the plane is continuous. So we'll say it's a polynomial in two variables, so it's continuous. When we write it out this way, ax plus by plus zz plus z equals 0, we recognize it. Actually, I'll simplify that. All right. We recognize it's a plane. All right. Now, something really nice happens here because the domain is easy to draw too. Right? What does y greater than or equal to x minus 2 look like? Again, what you do is you draw the boundary and then check each side of it, right? Y greater than or equal to x minus 2. What if I put the boundary y equals x minus 2? What does that look like? Oh, come on. Give this an algebra. Line. Yeah, it's a line, right? It's just y equals mx plus b with slope m equal 1 and y-intercept b equals minus 2. So at negative 2, there's an intercept, and then a slope 1, so it looks something like that. Right? That's that one. Now, if I put the other one, y equals minus x minus 2, similarly, it's a line of slope minus 1 and y-intercept minus 2, so it goes up something like that. And then the line y equals 3 is evident for the other boundary. It's just a horizontal line. And what you've got is a region with those boundaries. And then you check each side of these because on an inequality, what you're describing is all points on each side of the line, and because it's equals, you include the line itself. So I'll draw all these boundaries solid because, right, it's a non-strict inequality. I want to include the line itself. And then you look on each side of the line. An easy way to check is just check a point on one side of the line. Like check the easy point, 0, 0. Does 0, 0 satisfy the instant inequality? 0 greater than or equal to 0 minus 2. Sure it does. That means that I want to shade the 0, 0 side of this line. So I want to shade, if you like, shade this side of this line. Those are all the solutions to the first inequality. Y greater than or equal to minus x minus 2. That's going to be one side of this line. So I check 0, 0 here. And 0 is greater than or equal to 0 minus 2 is true. So I want to shade this side of this line. Right? And then y less than or equal to 3 is obviously the points down here. Then you say, what points have all three shadings? It's these in here. I'll draw it in red. The points that are on the correct side of all three lines, there's your domain. D is this big triangle. So that is indeed a closed bounded region, right? Doesn't go out to infinity, so it's bounded. Includes its boundary points, includes all three line segments. So it's closed. Now I can try and maximize or minimize this function over the triangle. And here's what it looks like. It's a plane over a triangle. So what do I know immediately about this? I don't even have to go back to that theorem. I can apply the following. Here's the triangles written in x, y, z space. I'll plot it. Looks like this. So it's in the xy plane. There's D down here. And what I've got is a plane over that looks something like this. It comes up here, maybe, over this point. And then it comes up here, over this point. And I'm trying to find the maximum and minimum of this plane over this triangle in the xy plane. What do I have to do? It's really easy. when you have a plane over a polygon down here, something with straight edge sides, the maximum and minimum are going to occur at corners. All I have to do is plug in the 3 corners. So this is called a linear programming problem. We have a linear function, ax plus by plus c, over a region that's bounded by lines. It's a linear programming problem. And people in business do these in multiple dimensions where you can't draw the pictures anymore, but it's an extremely important problem in business. There are whole software packages set up to solve this problem. In multidimensional space, find the corners of your domain and plug all of them in multi-dimensions to find the one that gets the highest point on the linear function that you're going to optimize here. So this is actually a famous problem, the linear programming problem. And so here, all we have to do for these linear programming problems, where you have a linear function over a region bounded by line segments, you simply check the corners. There's nothing more to it than that. We don't need that whole theorem we just wrote up. There aren't any interior critical points because it's a plane. And actually, you can have 2 corners that are both maximum, and then the whole line between them is a maximum. But there will be a maximum at the corner and a minimum at the corner, and then a consecutive corner being a maximum, and you take the whole line segment. The whole region could be a flat plane, and every point is a maximum, and that kind of stuff can occur. But I'll plug them in. The corners, if I set these equations equal, then I can probably view this one. So, x equals 0, y equals minus 2. So I just check f at 0 minus 2, what is it? I plug it in. 5 times 0 minus 3 times minus 2 plus 34. Let's see, it's 34 plus 6 is 40. All right. So it's 40 at the 1 quarter, and then I plug in f at the other points. This one, if you work it out, right, you've got y equals 3, plug it in here, you get x equals 5. So it's 5, 3. Similarly, plug y equals 3 in here, and you get minus 5 for x, 3. So you take f at minus 5, 3, that corner, f at plus 5, 3, just by setting the equations equal there. Now let's see, minus 5, 3, we got 5 times minus 5. Minus 3 times 3 plus 34. Let's see, minus 25, minus 9, minus 34. Plus 34 is 0. And then over here, I take 5 times 5, 5 times x, minus 3 times y, plus 34. So 3 times 3 plus 34. Let's see, 16 and 34 is 50, is there? 25 minus 9 is 16 plus 34 is 50. There we go. So we just check them all. The largest one is the max. You get max of 50. That's this equal. And then at the point 5, 3, one of the corners. And then there's a minimum of, what's the smallest number there's 0 at the point negative 5, 3. So my drawing is not real precise. It actually has the minimum of one of these. Let's see, this corner. And the maximum at this corner, but you still get the idea from there. Any questions on that one? That comes the biggie. The harder ones are where you have to, where you don't have a linear function like that. Let's try this one. Suppose I have f of x, y is equal to x cubed minus 2y squared on the closed bounded region, 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to 1, right? That's just the unit square including its boundary. You can read that off. So the region is really easy, just 0 to 1, 0 to 1 on each axis. This is your region D. But now this function is not a plane, it's something complicated, so we have to go back to the theorem. We need to check the interior critical points. And the theorem says the boundary points, but I'm going to say the critical boundary points, critical points along the boundary. Because what you can do is write parametric equations for the boundary. And from those parametric equations, get a calculus 1 problem to maximize and minimize a function of one variable. This is always one of the most tedious sections in the course this semester. But that's what the theorem says, that the max and min occur, since it's a continuous function that flows down a region. They occur either at an interior critical point or along the boundary, which we can check by checking the critical points along the boundary. Calculus 1. So what are the interior critical points? Remember how we find those? That was what we did last time when we were finding local max and min. What do you do to find critical points?
You take the partial derivative with respect to each variable.
Yeah. In calculus 1, you set the derivative to 0. Here you set both partial derivatives to 0. Why don't I have to worry about points where it doesn't exist? Maybe because those are also critical points. In this case, I don't have to worry about those because, again, it's a polynomial with two variables. It has derivatives of all order. There aren't any points where it doesn't exist. So the critical points, I just set both derivatives to 0, right? But in practice, you might have to check for those on other functions, whether they don't exist. All right, so partial with respect to x is 3x squared. Partial with respect to y is minus 4y. This equals 0 says x equals 0. This equals 0 says y equals 0. There's one interior point that's a critical point. 0, 0. And so you plug in the function at that point. F of 0, 0 is 0 cubed minus 2 times 0 squared is 0. That's one of the values you're going to check. And you're going to do just like calculus 1, or like we mentioned at the beginning here. In calculus 1, this problem here, where you had a continuous function of one variable in a closed interval, you found the interior critical points, you plug that in to get f of c, you plug in the endpoints, and the largest was the max, the smallest was the min. Same thing here. I'm going to find the interior critical points, the critical points along the boundary, plug all of them in and see which is largest, which is smallest. Right? So there's one point I need to check. The second thing is I need to look at the boundary. The boundary is long and tedious here, so watch my time a little. The boundary, you do this, I can break this into 4 pieces. How can I write this boundary, I'll let C1 parametrically, this side of the square. This is actually a hard part of the section. You do it the easiest way you can in practice. There's lots of ways to do it. The easiest way is to let x equal t and y equal 0, and let t run from 0 to 1, right? That will sweep out this line segment. Then I can call this side of the boundary. The boundary is the whole 4 sides of the square, but I'm going to break it into 4 pieces. C2, I could let x equal 1.
We can't see what you're.
Oh no, I'm right at the top. Thank you. Okay, so the bottom boundary, I let x equal t and y equal 0 as t runs from 0 to 1, and I will sweep out this boundary, right? X will go from 0 to 1 and y will remain 0. Over here, I'll let x equal 1 and y equal t. Let t go from 0 to 1, and now I'll sweep out this line segment, right? And then along the top here, I can call it C3. Easiest way I can think of to do that is let x equal t and y equal 1, and let t run from 0 to 1. And then C4, you let x equals 0 and y equal t. And again, let t run from 0 to 1. And then C, the boundary, or I'll introduce you to some notation. If you call this D, the boundary is often denoted DD. It's like the curly D there that we use for the partial derivative. DD, the boundary is the union of those, C1, union C2, union C3, union C4. And we've got to check all along the boundary. What a mess, right? There's 4 different pieces. But this is what you do. Along C1, you just check them one at a time. Along C1, we have the function f can be written as a function of one variable, right? We write f of x of t, y of t, because of the parametric equations. F is equal to x cubed minus 2y squared. So it's x cubed minus 2y squared, right? But along boundary C1, x is equal to t, and y is equal to 0, and so we get t cubed. Now you have the problem of maximizing and minimize t cubed, where t runs from 0 to 1 along that boundary, right? How do I find the maximum and minimum of t cubed when t goes from 0 to 1? It's just calculus 1, right? This is a continuous function of one variable in a closed interval. You find the endpoints, you find the critical points, you plug them all in, see which is largest, which is smallest, right? So I plug in 0 and 1, and I set the derivative equal to 0 to find the interior critical points, and I just plug all those things in. So check endpoints of this function of one variable. T equals 0, what was put here? T equals 0, t equals 1, along C1. At t equals 0, I get f equals 0 cubed. Right? T cubed is 0 cubed is 0. Along at t equals 1, f is equal to 1 cubed is 1. And this occurs at what? Well, if t is equal to 0, then along C1 we had, remember, x equals t and y equals 0. So we have, when t equals 0, we have 0, 0 as the point. And when t equals 1, we've got x equals 1, y equals 0. So this occurs, f is equal to 1 at the point 1, 0, the corner of the square. And f is equal to 0 at 0, 0, the corner of the square, right? So I checked out C1. These are the only candidate point values. The f has this point and this point, and you say along C1, you get a maximum of 1 at 1, 0. A minimum of 0 at 0, 0. Then you just have to do this for all four boundaries. So you're gonna look. Here's the maximum on this curve, the minimum. Here's the maximum, and here's the maximum, here's the interior critical point f value. And now I just have to do. Let's try C3 next, just for sake. You can do these in any order, obviously. So let's say along C3. Along C3, we have x equals t and y equals 1. And we got f, the function of two variables, can be written as a function of the parameter t. It was x cubed minus 2y squared. This time y is 1 and x is t. And so the function is t cubed minus 2. And so this is on the interval 0 less than or equal to t less than or equal to 1 on the parametric curve. So since this is a function of one variable on a closed interval, I check the endpoints. T equals 0, I get f is equal to 0 cubed minus 2 is negative 2. And what's the corresponding point on the boundary? It's, well, t equals 0, so it's 0, 1. Right? X equals t is 0 and y equals 1. And then at t equals 1, all right, then x is equal to 1 and y is equal to 1, plugging in. What I get is f equals t cubed minus 2 is equal to 1 cubed minus 2 is negative 1. So I check these values. These are the f values here. And there are no, I should have pointed out, there are no critical points of t cubed interior. So this was no interior critical points on C1. Same thing here. If you set the derivative to 0, interior critical points to this curve, so C3. We set the derivative equal to 0. 3t squared minus 0 equals 0. The derivative equal to 0. Tells you that t equals 0. There's no interior critical points except the boundary. So you just plug in the endpoints. Those are the possible values. And then you have to do this on all four sides. So the next one you do is along C2 and along C4. Along C2, we had x equals 1 and y equals t. F as a function of x and y, of t through x and y, is equal to x cubed minus 2 times y squared is now 1 cubed minus 2 times t squared is 1 minus 2t squared. And this is a function of one variable. On the closed interval, you can maximize and minimize it by plugging in the endpoints and checking the interior critical points. Endpoints, yeah, it gets to be t's. You got to break the boundary into 4 pieces, and on each one, write a parametric curve, do calculus 1 on it. Endpoints, you check at t equals 0, the endpoint of the interval. You get f equal 1 minus 2 times 0 squared is equal to 1. And this is at the point, well, let's see, x equals 1, y equals 0, plugging in t. That's actually the same point we checked before on the other boundary. At t equals 1, we get f equals 1 minus 2 times 1 squared is negative 1. We get that, let's see, at 1, 1. And then an interior critical points of this boundary, when you set f of x, f prime equals 0, you just get 0 equals minus 4t. Says that t equals 0. There's no interior critical points. It's a boundary point. So using calculus 1 analysis, we only have to check the endpoints on this. I'm about out of time, so I need to wrap this up. We'll just say similarly check C4. And we'll get no new important points. And now there is an absolute max. We already know by the theorem. How do I find the absolute max? I just look through all these numbers I circled. Here's the value of function at one corner is minus 1, and here's another one at 1. Minus 1 and minus 2. I go over here, let's see. 0 and 1. It looks like the maximum, the largest, and then there's an interior critical point where I get 0. So I just look at all the function values that I got. The maximum function value I got was 1. It occurred at the corner point, 1, 0. And then the smallest function value I got between the interior critical point and the boundary points was negative 2. It occurred at the point, let's see, here's 2, f0, 1. So at opposite corners, I get a maximum and a minimum for this function. There we go. And that's how you do those problems. They're pretty tedious, but you can see the nice, easy strategy of it. Thank you for your attendance. Go have a nice weekend.